This is the Chapter 1213 practice test walkthrough. Alright, so the matching, I'm just going to move through these pretty quickly. Your definitions, vocabulary, you want to make sure you have all your vocabulary terms down. So, kinetic energy is the energy of motion, that's F. Fluidity is the ability of a substance to flow and diffuse, J. Effusion is gas escaping through a tiny opening. A phase diagram is a graph of pressure versus temperature for a given substance. A manometer is a device for measuring the pressure inside a closed container. Boyle's law shows the relationship between pressure and volume of a gas, that they're inversely proportional. Gay-Lussac's law shows that pressure and temperature are directly proportional. Absolute zero is the theoretical point at which all particles are in their lowest possible energy states. The Kelvin scale, based on absolute zero, is a measurement of temperature with absolute zero at its lowest point. And standard pressure is 760 millimeters of mercury, or 1 atmosphere. In the multiple choice, we have 3 gases with a total pressure of 30.4 kilopascals. So we're going to be using Dalton's law of partial pressures here, which says that the sum of all the partial pressures is equal to the total pressure. So we know that the total pressure is 30.4, that one of the partial pressures for O2 is 16.5, and the pressure of the nitrogen is 3.7. So we're missing the third gas, or could be more than one gas, but the remaining gas or gases make up the difference between 30.4 and the sum of 16.5 and 3.7. So you take 30.4, subtract 16.5, subtract 3.7, and you'll get the final pressure, which is 10.2, and that is answer choice C. Which of the following is not considered a fluid? Okay, liquids and gases are fluids, which means that solids are not considered fluids. So the answer choice here is B. Fluidity, the ability to flow and diffuse, so move from one container to another and mix together. Of the substances listed, which has the highest kinetic energy on average? Well, gases have the highest kinetic energy overall, and liquids are in the middle, and then solids are the lowest. So in order of kinetic energy from least to most, it would go solids, liquids, then gases at the top. So that is answer choice C for this question, 13. Number 14, which of the following changes in state or phase changes requires that energy be removed from the substance? So we're going from higher energy state to lower energy state. Well, melting is something that requires an input of energy. So is vaporization, and so is sublimation. All of those changes, melting is going from solid to liquid, vaporization is liquid to solid, sublimation is solid directly to gas. All of those require the input of energy, which means the only choice left is B. But just so you make sure you know, condensation, freezing, and deposition, those 3 phase changes all require removing energy from the system. Number 15, which is the state change that occurs when a gas becomes a solid without becoming a liquid first? Well, here's all your changes. You've got solid to liquid is melting, liquid to gas is vaporizing or boiling, solid to gas directly is sublimation, and then gas to liquid is condensation, liquid to solid is freezing, and then the last one, which the question is asking about, gas directly to solid, is called deposition. So deposition and sublimation are opposites, melting and freezing are opposites, vaporization and condensation are opposites. So make sure you know the names of all these phase changes. Number 16, which gases will diffuse slower than C2H6 if they're all at the same temperature and concentration? So what you really need to remember here is that the rate at which gases will diffuse is related to their molar mass. Heavier gases, heavier substances diffuse more slowly. So first you need to figure out, well, how much is the molar mass of C2H6? Okay? Which has the higher molar mass than the one in the question? Well, C2H6 is 2 carbons, 12 apiece from the periodic table, plus 6 hydrogens. Each of them has a mass of 1. So you add those numbers together and you get a total of 30 grams per mole. So you're looking for the substances in the chart above that have a mass greater than 30, and that would be numbers 1 and number 4. So your answer here is D. Okay, so this is a phase diagram question, and there are 3 of them. So you use this same diagram to answer the following questions. What state of matter will this substance be at a temperature of 128 Celsius and a pressure of 0.8 atmospheres? So that point, first thing you need to do is find that point. 128 Celsius and 0.8 atmospheres is right about there, give or take. And that means that it is in this region on the bottom right-hand side of the table. So now you have to remember what those regions mean. Well, this is the solid area over here. This is the liquid area. And then this is the vapor or gas region. So that point with those conditions is in the gas or vapor region. So you're looking at answer choice D here. Okay, another question on the same phase diagram. Which is the point at which this substance will freeze at normal atmospheric pressure? Okay, so normal atmospheric pressure, first of all, is 1 atmosphere. So that narrows it down right away to either choice B or choice C. And we need to choose between the 2 temperatures. So what you need to remember is that freezing is the transition from liquid to solid. So we're transitioning from that middle area to the the left-hand region, and we're looking along this line, okay, this line of 1 atmosphere. And where does it cross from liquid to solid along that line? Well, it crosses right in here, okay, and if we track down from that point, it's between 80 and 85 degrees Celsius. So that puts us in the 84, which is choice B. Okay, one more question on this phase diagram. If the pressure of the substance is held constant at 1.6 atmospheres while the temperature changes from 0 to 100, what change in state will occur? So here are the 3 regions, solid, liquid, gas. And we're going to start at 0 Celsius and 1.6 atmospheres, which is this point over here. And we're going to move from left to right. That's what increasing the temperature does. Starting at that point there, 1.6 and 0, we're going to move from left to right to this point over here, which is 1.6 atmospheres and 100 degrees. Well, if we follow that line, moving across, what happens? We move from the solid area on the left to the liquid area in the middle, and we find ourselves crossing that phase barrier, and what that is melting. Okay, melting is what happens when you go from a solid to a liquid. So that's answer choice D. All right, moving on to some problems. If a gas occupies 160 milliliters at 10 degrees Celsius, what volume will it occupy at 35 if the pressure is unchanged? So we're taking pressure out. It's a constant, so pressure is not a variable here. We've got a volume 1, we've got a temperature 1, and we've got a temperature 2. So we're trying to find the second volume. Okay, that's the question. What volume? Well, that gives us this formula, which is Charles's law, volume and temperature relationship, and then we need to plug in the numbers that we have in the question and solve for V2, which is the unknown. Don't forget, when you're doing all of these problems, anytime you have temperature and it's given in Celsius, you must convert to Kelvin by adding 273. So plug in the numbers. 160 was given, the temperature we were given was 10, so we add 273 and make it 283 Kelvin. And then the volume 2 is what we're trying to find. And our second temperature is 35 Celsius, which 35 plus 273 gives us 308. Cross multiply and you end up with 160 times 308 divided by 283 is equal to 174 milliliters. So that is the answer that we're looking for here. 174 milliliters is the final volume. 22. Bug spray says keep its temperature less than 80 because it will explode or might explode. So we're trying to figure out if we measure the pressure at 21 Celsius, which is, around room temperature, and it's 3 atmospheres, 3.05 atmospheres at room temperature, what would the pressure be at that 80 degree mark that might make it explode? Well, we've got a pressure and a temperature to start with, and we've got a final temperature, and we're trying to calculate the unknown which is the P2. Okay, so we've got this time pressure over temperature, which is Gay-Lussac's law. Okay, and we've got a P1, a T1, and a T2, and we're trying to find the P2 there. Plugging in the numbers, don't forget to convert to Kelvin. Okay, so 3.05 atmospheres over 294, which is 21 Celsius, equals the unknown P2 divided by 353, which is our 80 plus 273, cross multiply, and 3.05 times 353 Kelvin divided by 294 Kelvin equals 3.66 atmospheres. And again, just to check it, you're increasing the temperature, and therefore you should be increasing the pressure. So at least our answer does make sense in terms of going in the correct direction. Okay, balloon purchased at a football game in Denver. So high altitude. The volume of the balloon is 21 liters. The pressure up there, way up in the mountains, is 0.82, so lower than normal pressure at sea level. The temperature there is 10 degrees Celsius, which is kind of chilly. When we bring it home to Norwell at roughly sea level, the pressure is 1.02, so slightly above standard pressure. And the balloon has lost some of its volume. It has collapsed to a volume of 17.8. So what's the temperature? Well, we've got a volume, a pressure, and a temperature, and then we're going to change the pressure and the volume. So we've got 5 variables here, which means we need to use the combined gas law. So we're going to plug in all the numbers we have and solve for the one that's missing, which is going to be the T2. So there you go. There is your P1 and V1 on the left over T1, which is 283, so 273 plus 10, always convert to Kelvin. On the right hand side we had the 1.02 atmospheres times 17.8 liters as our volume, but we don't know the temperature, so that's what we're trying to solve. Cross multiply, and you end up with 1.02 times 17.8 times 283 divided by 0.82 times 21. And when you do all that, it comes out to 298 Kelvin, which is 25 degrees Celsius. Okay, 60 grams of N2 nitrogen gas occupies 39.5 liters at a temperature of minus 12 Celsius, so below freezing. What pressure in kilopascals will the gas be at? Okay, well, we've got grams, we've got liters, and we've got temperature, and we're being asked to find pressure. Well, we don't have any equation that has grams, liters, temperature, and pressure. But what we do have is volume, temperature, pressure, and number of moles. Okay? But we don't have the number of moles. We have the number of grams. We can use the number of grams to find the number of moles because the mass divided by the molar mass of an element or compound is equal to the number of moles. So we can take the grams we were given and convert that to moles, and then we can use that in our ideal gas equation above. So we're given 60.9 grams. The molar mass of nitrogen gas, N2, is 28 grams per mole. Divide that out and you get 2.175 moles. Now we can go up and solve the ideal gas law up here. So the pressure times 39.5 liters equals the number of moles, 2.175, times 8.314 times 261 Kelvin. Why did I use 8.314 for R? Well, because the question is asking us to give us pressure in kilopascals, so that's the unit you have to use for R, or the value you have to use for R if you're talking about kilopascals. So if we do that out, we end up dividing by 39.5, and that gives us a pressure of 119 kilopascals. All right, number 25. We have a volume of 125 milliliters containing 3.22 grams of hydrogen and 11.56 grams of oxygen at 5 degrees Celsius. What is the total pressure in atmospheres of the cylinder? Well, again, we've got a volume, grams. Only this time we've got grams of 2 different substances. We've got a temperature, and we want the pressure. So we're going to go back to that ideal gas law. The only trick this time is we've got two substances, so we're going to have to find the number of moles of hydrogen and the number of moles of oxygen. The good news is once you get it converted to moles, all gases behave the same, so all we have to do is add together the two answers we get for moles and then plug that in for our N in this question. So we're going to take those two gases, right, convert hydrogen to moles, 3.22 divided by 2, that's what hydrogen gas would be, and we get 1.61. We take oxygen, the 11.56 grams divided by 32, O is 16 times 2, 32, and you get 0.3613. Combine those two, and our N in the equation is going to be 1.97 moles. So now let's go back to the top. We've got pressure that we're trying to find this time again. We've got a volume of 125. We've got a temperature of 5 Celsius, which is 278 Kelvin. Always convert to Kelvin first. And this time we're going to use 0.0821 for R because the question gives us, wants it in atmospheres. So plug in all those numbers. I'm converting to liters because that's what the calculation needs to be in for the ideal gas law, so just divide by 1,000 rather, and you get 0.125 liters. Put all that in there, divide by 0.125, and you get 360 atmospheres, a very, very high pressure. All right, 10.5 liters containing 9.62 grams of a gas at 50 Celsius and 6.25 atmospheres. Calculate the density. Well, this is pretty straightforward. Density equals mass divided by volume. So we've got a mass of 9.62 and a volume of 10.5 liters. Divide the two numbers together. The density is 0.916 grams per liter. Now we want to calculate the molar mass. Okay, and the molar mass equals the mass divided by the number of moles. So we need to find the number of moles that are contained here, and then we can use that and the mass that we have in the equation or in the problem up above to find the molar mass. So we need moles for the ideal gas law. We've got pressure, we've got volume, we've got temperature, and that we can find the number of moles through that. So 6.25 atmospheres, 10.5 liters is the pressure and volume. We're going to use 0.0821 because it's in atmospheres, and the temperature is 323 Kelvin. We divide all that out. The number of moles is 2.47. So 9.62 grams divided by 2.47 moles means that the molar mass is 3.89 grams per mole. Oldies but goodies, what type of reaction is iron plus sulfur produces iron sulfide? Well, you've got two reactants and one product. Two or more reactants with one product is going to be synthesis every time. And how many significant figures does the number 1500.40 have? Well, this is a non-zero, that counts. Non-zero counts. These two zeros are in between other numbers, that makes them sandwich zeros, so they count. That's not a zero, and this is a trailing zero with a decimal point. So all of the digits count, which means your answer here is 6.